about discrete probability. So now we're going to start to speak a bit about statistical mechanics. You already had a week about that, and probably you did statistical mechanics before. For you, what are the keywords, like what are the key notions in statistical mechanics, if you had to select a few words to describe the kind of systems that we study with statistical mechanics, and what kind of things, of questions we would like to answer? How would you describe that? Like, if you had to explain that to your little brother or sister, what is statistical mechanics? How would you do? It's important sometimes to wonder this kind of things, because if you can explain that to someone that doesn't know anything, it means you know they thought about it enough so that you can simplify it. It's Einstein, I think, that said that if you're not able to explain something, you don't understand it. So sometimes ask yourself, can I explain that to someone that doesn't know about it? Can I speak 5 minutes or 2 minutes about what it is? And actually, it's very important for you. So I wrote a long introduction that you can find in the notes, so I won't repeat everything. You can read.
Are we just supposed to answer?
When I ask a question, yeah. Essentially. Yes.
I would probably explain statistical mechanics as the field of physics that explains how a collection of different particles, there are different types of particles in physics, how each of those categories work differently.
Okay.
So, I mean, in more difficult terms, we call them macroscopic quantities, like observable, but the microscopic particles that make up those, that exhibit those properties are basically particles. So, I mean, for example, we are 4 people here, all of us are different in some way. So, whatever our personalities are, we're kind of measuring those, but we do. And that's it.
Okay. That's one way. There is, I agree, with many things. Do you have something to add?
For me, statistical mechanics is description of the system based on the entropy and the energy of all the system, how the particles can be exchanged for some time, for some modification of temperature and the volume of.
Okay. But imagine you're talking to someone that doesn't know what entropy is, and I'm not sure at the moment. Do you understand really what entropy is? I think it's quite a deep concept. So if you had to make it simpler.
The entropy is.
Let's not talk about entropy right now. We will discuss a lot entropy, but what I'm asking is, can you describe that to a kid, to someone that doesn't know much about physics, no idea what entropy is, with simpler words?
Yeah.
What are the key notions?
The heat of the system.
Okay, but the heat is a very abstract concept already. It's you get up, the way I would describe that to a kid, one first notion that would come in my mind, which is really at the core of statistical mechanics, is the notion of what we call phase transition. If you say that to a kid, he has no idea what it is, but you can just tell him, when you boil your water, you pasta, you're in Italy, something happens above a certain temperature, the system changes. And this is what you want to understand with statistical mechanics, is this. So what happens to this large ensemble of molecules, so that at some point they kind of globally agree to change state. Okay. This is what we really want to understand in statistical mechanics. There are many other things we want to understand, but this is one really of the core question, at least in equilibrium statistical mechanics, which is what on which we focus in this course. We will also do non-equilibrium things. This is a different part. This is not what concerns us, but if you have to say that to someone, why and how complex systems change their behavior when you perturb them, when you change some parameters. And you give an example of phase transition, like water boiling or whatever. Okay. This is the way I describe it to someone that has no idea what statistical mechanics is. And so, really at the core of statistical mechanics is that we do not care about the details of the system. What we care about are really global quantities, what we call these observables, these order parameters, that describe the system as a whole, at the global scale. Okay? We do not care about the details of what are the trajectories of each particle, and this is not what we're interested in. Okay? And even if, let's assume that for some reason you would be interested in the single trajectories of each particle, because at the moment we're talking about particles. At some point we'll discuss about other things, but let's focus here on particles. Let's say that for some reason that I don't get right now, but maybe you are interested to actually describing really the microscopic dynamic of all particles. Like there are two issues there. We're talking about the Avogadro number of particles, okay, which is 10 to the 24, 10 to the 25. So it's like it's 100. It's 100,000 billion particles, okay, which is a huge number, okay. So there is first a computational issue. You will never have a computer able to solve the Schrödinger equations or whatever microscopic dynamics, whatever equations that describe their dynamics. You cannot solve all that together. They interact in some complex way, but the system is just too complex. And let's even go further and assume that you have such a computer. There is another problem, is that if you want to store all this information in memories like this computer, in SSD memories, in modern computer memory, you will need a volume which would be bigger than the observable universe. Okay? So what I'm trying to convey here is that it's not just, statistical mechanics is not just a kind of approximation. There is a fundamental barrier that prevents you to describe the system at a microscopic level. First, you're not interested about that. And secondly, anyway, you cannot. So you really need to resort to something else, which is statistics and statistical mechanics. Okay? So, also I like a quote by a Nobel Prize, whose name is Philip Anderson, that said something very short and that contains a lot, that describes statistical mechanics in 3 words exactly, which is more is different. So what does that mean? It means exactly what I said. It means that you cannot, it doesn't mean what I said. What does it mean? It means that anyway a complex system, which is made of very many interacting agents, particles, elements, okay, cannot be described as a collection of single agents, single particles. You really need to consider the system as a whole, because you have new phenomena that emerge, and we call that emergent phenomenon, that really come from the complex interactions between these very many particles. And very many is here very, very important. Things are different if you consider even 1,000 particles. Maybe this is not a complex system, it's quite complicated, but really the complexity that makes phase transitions happening and the statistical description becoming exact is really to have tons of particles. You really need to go to huge numbers. Okay? And thanks to statistics and what we call the concentration of measure, which is the fact that If you have very many random variables that interact, you have kind of averaging of the details that disappear. And what remains is a deterministic behavior. So you can describe a very complex random system because actually statistics become exact in this limit when you have so many of these particles. Okay. But you really need to consider them together. More is different. Okay? You cannot try to divide the system in subparts and to understand them individually, and then to combine this knowledge, you need to consider all of them together. Okay. And so the typical emergent phenomenon is a phase transition. The fact that a system radically changes its macroscopic behavior when you tune some external parameter, some control parameter, like the temperature or whatever, depending on your system, is an emergent phenomenon. Okay? There is no notion of phase transition if you consider 10 particles in a box. What does it even mean for 10 particles to be in a gas or solid state? You need to consider a lot in order to have a meaningful notion of different phases and therefore change between phases. So there's phase transition. Okay. And so the point of the course also is to realize that this notion of emergence, and phase transitions, and so on and so forth, is kind of universal. Okay, it is absolutely not restricted to condensed matter physics and the classical systems that you've seen during probably your course in statistical mechanics. By the way, who had a course in statistical mechanics? You? Statistical mechanics.
You studied it, right?
Yeah. I studied statistical physics before.
Yes, so this is what I'm asking.
Yes.
Statistical mechanics and physics is the same.
Statistical mechanics and statistical physics is the same.
It's the same thing.
Why do you say statistical mechanics?
No, it's the same thing. Okay, so you all had some basics. No, you didn't. And statistics, like just a course about statistics?
Yeah.
Yes.
Actually, when we studied the system here, something like different than the statistics I studied before, statistical physics. Because we learn more about Boltzmann, Boltzmann, Felix,
Yes.
all that sort of thing. But actually, it's different.
What do you mean it's different? It's different than what?
Since actually we talk about two systems, they got two systems. Yeah, it's different. I didn't study this thing before.
So which thing exactly I didn't understand? You studied the Fermi-Dirac statistics,
Yeah.
you studied the Boltzmann distribution,
Yeah.
so you did statistical mechanics. Okay. So what I want to convey is that these tools that you learned to study condensed matter physics, because the models that you studied were coming from condensed matter, it was particles, can be extended to study way more stuff. Okay? So I don't know if you've seen, but I sent you a mail. I wrote this thing that I finished today actually for a popularization journal, and I think it would be useful for you to have a look. And in particular, this is much more detailed, the notion of the base formula that yesterday I vaguely approached without much success because it's a deep formula. And here maybe you can have a look in more detail what it means. And also I tried to show that statistical mechanics can be used for and in the context of reconstructing signals and signal processing for statistical inference. Okay? It's directly connected to this course. Yes.
In the notes that you sent us, you said that we can attempt McKay's first few chapter exercises.
The David McKay, yeah?
Yeah, but when I opened that book, it was pretty different from what we're doing right now.
So you will show me which chapters, but there are chapters on just basic probabilities and things like this. So
the first chapter, there has been, like it was probability, but they were only taking information theory. So.
Okay, but this course is also about information.
I know, but we haven't gotten there yet.
Yeah.
So maybe after we.
Yeah. right. So essentially, statistical mechanics is a way to link your microscopic knowledge of a system, that is the equations that describe the particles at the single level and the way they interact, okay, to the macroscopic description through statistics, okay. All right, so you had this approach with Roman where you started from the microcanonical ensemble, okay, which is essentially particles in a box which exchange absolutely nothing with the rest of the universe. So their energy is constant, okay. And so what is the statistics that describe this system? So what is the probability distribution that describe the microstates in this case?
The formula?
I'm not sure you need a formula, just in words.
Yes.
No?
Could you repeat the question?
Yes, I want to know, just to check if some basic notions that you learned or recalled with Roman are still there. So in the microcanonical ensemble, which corresponds to particles that are totally isolated from the rest of the universe, that do not exchange any form of energy, and number of particles is fixed. What is the probability distribution that describes the microstates in this case?
Binomial distribution? Or are you meaning about the number of states?
No, I want to know what is the probability in the microcanonical ensemble to find the system in one given configuration.
1 over the number of states.
Yes. So when you have no exchange whatsoever with the rest of the universe, okay, the fundamental postulate of statistical mechanics is that, in this case, you know nothing about the system, because it exchanges nothing with the rest of the universe. And so the best you can do is to assume that all the states are equiprobable. Okay? So the distribution is the flat distribution. All the states have the same probability. Okay. Is it a discovery, or did you understand that?
To be honest, we didn't really understand. I did not really understand what Roman said.
Okay. All right. So now, in this microcanonical ensemble is the simplest setting, but it's not always the proper one to describe the system under study, and it's not always the more practical, because the fact that the energy is constant can make the computation of the partition function, that is the number of accessible states to the system, difficult, because you need to sum over all possible configuration such that the energy is fixed to an exact value, to a constant. And so it's a complicated combinatorial problem. Okay? Okay. So one way to relax this constraint is to say, that actually you allow the system to exchange energy with the rest of the universe. Okay? So it's like now the walls of the box, they let heat go through. Okay? So the system is not anymore, does not have any more fixed energy. It has a fixed average energy. Okay. And the average energy is fixed by the temperature of the external world that we call the external bath. Okay? So the temperature is a parameter that allows you to control what is the average energy of the system, of the particles that are inside the box. Okay? All right. And then I don't know if you went until this, but there is also, in case you will have heard about that, there is a so-called grand canonical ensemble, where you also allow the number of particles to change, to fluctuate. So the number of particles in the box is now changing. It's like if you open even the box, then you can exchange particles with the outside world. Okay? But in many situations, and in particular outside of physics and in the context of inference, the context of computer science, in the context of economics, in many contexts, actually it is sufficient to describe things using the canonical ensemble. So what is the probability distribution of configurations of the system in the canonical ensemble? At equilibrium.
Boltzmann distribution.
The what?
Boltzmann.
Yes, it's the Boltzmann distribution. Okay?
Boltzmann-Maxwell.
Yes. Sometimes it's called Boltzmann, sometimes Boltzmann-Maxwell, sometimes Gibbs-Boltzmann, sometimes just the canonical distribution. All that are just names. Okay? It's exponential minus beta h over z. Okay? So, right. So in this course, we'll start from there. By definition, the system will be at equilibrium. So, and by system, what I mean, let's be a bit precise with all what we said yesterday. This will be an ensemble, okay? So an ensemble, we said, is a random variable. Okay, so here I will put a bar. Sometime I will forget it, but just to emphasize that this is a vector. Okay. It has a space of configurations, or elementary outcomes, if you want. In this case, I will call it xn, where this n here is to recall that we're considering n variables, n particles, if you want. So this vector with the size, this random variable, is a random vector of size n. And it has a probability distribution, which will be the Gibbs-Boltzmann distribution. Okay, so here this x is x1 until xn. So these, if you want, are our degrees of freedom. This could correspond, for example, to the positions of particles, or if they're binary, that could be the spin. It could be some spins, okay? And the outcome of this random variable is little x. You remember the two notations. And this is the configuration. Okay, think about like if this space is Rn, sorry, P omega, you mean this probability? This could be positions of particles. If instead you consider minus 1, 1 to the n, these are spins, okay, etc., etc. So this distribution here is the Boltzmann distribution. And so we will assume, we'll define, I'm not sure to understand what you mean by how we read it, so I will say that the system is at equilibrium if the measure sorry, the probability distribution, the law that describe it, that if I write things completely is that I will write more shortly like this, is what is exponential minus beta, some function h that depends on this configuration over z. What is z? It's the partition function, and it is the normalization constant. So how do we normalize the probability? Just sum the numerator over all configurations. Okay. So here I will write everything with sums. So implicitly I assume that the random variable is discrete, because this is what will be mostly concerned in this course. But of course, if things are continuous, you replace that by an integral. Okay. And this function is what? It is called the Hamiltonian. This is the energy function. Okay. This is a function from the state of configurations to a scalar. Okay, it outputs a number. It's a number, and this is the energy of the system. And this function is called the Hamiltonian. Okay. So essentially, that's it. Our definition. We will be concerned with systems, probabilistic systems, which have a law of this form. Okay. And actually, with these laws, you can describe infinitely many different systems that are also not usual physical systems. Okay, so this little x is a configuration, or what you would call also the microstate. Okay. All right. So what happens to this law? So what is the name of this beta first? What is this beta?
Boltzmann constant.
No, this is not the Boltzmann constant.
1 over kb t.
Yes, is 1 over t times the Boltzmann constant if you're considering a physical system.
Yeah.
But here this is true for a physical system. Okay, it's the inverse temperature, and the kb here is to make the units to match. Okay, but this is just a constant. So yes.
We have the name.
Sorry.
We have the name. Beta have the name.
Beta, I don't know.
That's a name. No.
Beta, no, beta is the inverse temperature. Okay, but we can keep the interpretation of inverse temperature in mind, but we can also just consider this parameter beta in itself. But what matters is what happens when this beta changes. Okay, this is how we understand the meaning of this object, is by understanding how it affects our system. And when we say the system now, the system is fully described here. We have defined the system. This statistical mechanics, once you have written the Hamiltonian, this is the system. Essentially, all the information, any question you want to ask about the system will be deduced in some way or another from this Hamiltonian. Okay? So this energy function defines the system. So in statistical mechanics, when someone writes an Hamiltonian on a blackboard, this is the system. Okay? This defines what you are studying. Okay? And the behavior of this system is dictated by a certain probability measure, a probability law. So sometimes I say measure. A measure is again a probability distribution or law, or that is the same thing. You need to get used to that because you will hear. I do that a bit on purpose because if one day you hear measure, you're not like, well, okay, when someone that does statistical mechanics or probability, whatever, say a measure, we always mean a probability distribution. So we have defined the system thanks to the Hamiltonian. We know how this system behaves from a probabilistic point of view, because now we have associated the measure to the system. a law, which is the Boltzmann measure. So essentially, now we just have to compute and get what we want to get from that. Okay. So one first thing I want to understand with you is what happens when we change this beta. So let's see what happens when beta goes to 0. So so we have our measure exponential minus beta hx. So now I will drop the bar. Okay, I'm always talking about a vector. This little x is a vector of size n. Okay. So what happens when beta goes to 0 plus? So 0 plus means to 0 from above. It stays positive. Okay. This thing cannot be negative, the temperature.
1 over n.
So this tends what? Sorry?
1 over n.
1 over n?
Yeah.
So this tends to 1 over z evaluated, because this, of course, this beta is this z is a function of beta, evaluated in 0.
Yeah.
So the measure, the law, becomes flat. Okay? So at infinite temperature, okay, it's like the system was behaving like a micro-canonical ensemble. It becomes flat. All configurations, they have the same probability. Okay? Okay. And what happens, more interesting, when beta, so beta goes to 0 means infinite temperature. Okay, at very high temperature, essentially the particles, the temperature is so high that the interactions between the particles that are dictated by this energy function, by the Hamiltonian, do not matter anymore, because the thermal path is just moving around these particles so high that it's like if they were not interacting anymore. And so the particles, they become free of each other. They don't see themselves anymore. Okay, they become independent. Okay. What happens in the other extreme at 0 temperature? So when beta goes to infinity. What?
0.
So what is 0?
The fraction should be 0.
So then this number becomes 0.
Yeah.
So you're telling me that all configurations at 0 probability. So when you say something, try to think about what it means. Okay? Is it meaningful that all configurations become impossible because they have 0 probability? So what does it mean for a system to have 0 probability to be in any state? It means nothing. So maybe this is not the answer. So the exponent, I agree with you, the exponent goes to 0, but the denominator is what? And let me write that again explicitly. It is a sum over all possible states of something, and this something, the numerator, will also go to 0. So you have a 0 over 0 essentially, so you know, things are a bit subtle. But one trick here to understand what happens is to rewrite this as exponential minus beta the energy minus what I will call h min. What is this h min? Is the minimal energy. This is the minimum of the function of the Hamiltonian. Okay? So h min, by definition, is the minimum with respect to x of hx. It's a number, okay? All right, and you see that I can do that because essentially I'm doing it at the denominator as well, and because this h mean does not depend on x, if you want, what I just did is to multiply and divide the numerator and the denominator by the same thing. So I just multiply by 1. This thing goes out of the sum because it does not depend on x. So it simplifies with the numerator. It's just a constant. So here I did nothing. I just did a trivial manipulation. Okay? I multiplied and divided by the same number. Okay? But now it becomes clearer what happens. You see that if I call delta hx this quantity, okay, which is necessarily positive because we have defined h mean as the minimum energy. You see that when beta goes to infinity, if this delta h is positive, then you get 0. Because exponential minus beta times something positive with beta going to 0 indeed goes to 0 exponentially fast. Okay? But if hx is equal to h mean, then you get exponential of 0, which is 1. Even if beta is very large. You see? So what does that mean? It means that all the configurations that have an energy even slightly bigger than the minimum energy, they have 0 probability. Okay? While the states, when I say states, I mean microstates or configurations that have minimum energy, they count for 1 unit in the partition function. Because I get exponential of 0 means 1. You see? So this tends to, when beta goes to infinity, to 1 over z plus infinity. And here I will use a notation I introduced already. Is this notation clear, what I wrote here? Or these are, so this thing is the indicator function that we already defined. It is equal to 0 if what is inside is not true. It is equal to 1 else. Okay? So what is written inside this indicator function? It is written that x, the configuration, belongs to a set. When we have curly brackets here, we mean a set, an ensemble. Okay? Not an ensemble in the probabilistic sense that I defined. Just mean a set. Okay? And what is this set? Do you know this symbol argmin? What does it mean?
Argument.
Argmin is the argument minimizing something. So argmin of with respect to x prime of hx prime means this is the set of configurations that are minimizing the Hamiltonian. Maybe there is just one, maybe there are 34, maybe there are 10 billion. We don't know. but we know this set exists. Yes.
X prime is just
X prime here is just a dummy variable. I can call that A if you want, or whatever symbol you want, as long as it's an n-dimensional vector. Okay. This X prime belongs to the space of configurations. Okay. But this X prime is a dummy symbol. It's just that I don't want to use X again because the X is outside this set. Okay. So this is the set of configurations whose energy is minimum, is equal to H min. Okay? And this Z infinity then is the normalization, means that I must sum the numerator over all configurations, and therefore, what is it? This Z is the sum over all X this Z is the sum over all X of this set that I have, and therefore it is each time a configuration has minimum energy, I count 1, otherwise I count 0 in the sum. And so this is just the number of X's such that, or I will write this with a, this is the cardinal of the set of X's such that H of X is equal to H min. Is it clear? And this set, these X's are called set of ground states. What we call a ground state in statistical mechanics means a configuration whose energy is minimum. It's not this, it is of course very stable, okay? But if you have non-zero temperature, you will not always find the configurations in the ground state, they fluctuate, that's all the point. They fluctuate according to the Gibbs measure, so that when beta is not equal to infinity, you can be in any configuration, but the probability to be in a given configuration is given by this measure. Okay? Is that clear? If you take a system at non-zero temperature, at finite temperature, you have a probability to find it. If you observe it, if you look at the microstate, it can be in any microstate. It's just that there are some that are less probable and some others that are more probable. And yes, the ones that have an energy which is lower, they have a higher probability, because we see that if H here is small, because we have a minus in front, this exponential will be bigger than when H is large. So indeed, the energy controls the probability of being in one configuration or another, okay? But if beta is finite, all configurations, they have a non-zero probability. So that some have bigger probability and some others have lower probability, okay? But really, in the limit of zero temperature, the only states in which you can be are indeed the ground states. The system is frozen, there is no thermal fluctuations anymore, no agitation, the system is still, as stable as it can be, and if you are trapped in one of the ground states, maybe there are many, but you selected one, and you will never move from there, because there is no temperature to allow some fluctuations to jump from this ground state to some other state. You are frozen, okay? Okay. here I didn't write it explicitly, but yes, when beta goes to 0, this is the partition function, is the cardinal of the phase space, the space of configurations. Okay. All right. So let's now define actual statistical mechanics model and continue our discussion on interpreting what happens or when we change the temperature or other parameters that define the Hamiltonian. Okay? So it's much more difficult to work actually with the whiteboard like this than on an actual factor. I find. Okay, so I want to start with one of the simplest statistical mechanics, discrete statistical mechanics model. So from now on, like I said, we will always focus on systems described by a Gibbs measure, okay, a Boltzmann distribution. Okay, Gibbs measure is also the same as Boltzmann distribution. Okay. Actually, it's more general, but when I say Gibbs measure, what I mean is a Boltzmann distribution. So don't get confused. If at some point you get confused, ask me. Okay, I use many different ways of calling the same thing, but these are just for. We'll always focus on systems described by an Hamiltonian and whose probabilistic behavior is given by a Boltzmann distribution. Okay, we will not go away from that. Okay, so let me define the so-called lattice gas. Did you do it already? No, you didn't do the lattice gas. You did probably the Ising model a bit? Not even, okay. That's perfect. But have you seen, independently of the course by Roman, the lattice gas or the Ising model in your curriculum? And for those that are online, have you ever heard about the Ising model? Did you compute anything? Do you have some experience with the Ising model?
Not yet.
5 years ago.
5 years ago?
Yeah.
Okay.
For me, I've never heard about
Okay.
Ising.
So, in physics, we like, and this is one of the strengths of physics, from my point of view, that we like having what we call paradigmatic models. Some models that are simple enough to be tractable, to compute things, okay, to be analyzable, thanks to techniques of statistical mechanics in this case. But at the same time, that are very rich, that have a behavior that and a phenomenology that applies much broader than this specific model. And one of them is the so-called Ising model. If you want, this is the ultimate. You can describe, if I'm a bit extreme, whatever you're thinking about the complex system, you can describe it in some way with the Ising model. This is a very universal model, and its phenomenology and the things that you can compute and understand thanks to this model, they then apply much more broadly. So really, this is one of the models you must, as a physicist, master. Okay. And one version of the Ising model is the so-called lattice gas. It's perfectly equivalent to the Ising model, but I will start defining this one because it has a nice interpretation. So consider a grid. Okay. And all the allowed positions on this grid defines, we call that, you have a set of positions, okay? Let's say it's a box like this, okay? And at each of these positions, you can have a particle or not, okay? All right, so the way we describe this system, it's thanks to a configuration, again. And let's say that in this box here, there are n possible locations, okay? Let's say that the box is of size square root n by square root n and is discretized. You have n possible positions, okay? And so this configuration describes these locations, and it will belong to the space of configuration in this case, which will be 0, 1 to the n. And 0 simply means that at this location, if xi is equal to 0, there is no particle at this position. While if it is equal to 1, there is a particle. Okay? So think of a surface on which you can have particles that are there or not, okay, that can move around. And we will describe the statistics of these particles on this surface. Okay? So now we need to define the system, and like we said, what does it mean to define the system? It means to associate an Hamiltonian to the system. Okay, once this is done, we have everything. We just need to compute. Okay. So the Hamiltonian of this system will be given by hx, and here I will write dot, comma, j, and mu. And when I put a dot, comma here, it means that these are other parameters which are not describing the configurations, but which are parameters that define the Hamiltonian, that are parameters of this function. Okay? They're just quantities which appear in this Hamiltonian. And this will be sum over all let me write it coherently with my course, with my notes. I will directly, okay, I will make it simple directly. So I will write, I will write the simplest case. Okay, so this notation means what? It means I sum over all edges. So get used to this word. Edges means what? Just means here two neighbor locations. Okay, you can think of this grid as what we call a graph. Just means a network of nodes that are connected by edges. Okay, and this sum means here that I sum over all possible edges. And here, the edges on this specific example just means all the close by neighbors. So each location described by xi, it has 4 neighbors in what I wrote. Okay? And here, I sum over all vertices, which I also call nodes. Vertices and nodes are the same thing. And it just means the locations. All the positions in this grid, in this graph. Okay? On purpose, I'm using the vocabulary with which you're a bit less familiar to make it a bit more abstract, because that's also the point of this course, is to see that the techniques that I'm talking about right now can be applied to more generically. You can think of this as an actual surface, a real physical surface, that can define a generic graph, like just a generic structure of interactions between variables. Okay, so here we have a graph.
Isn't it like graph theory?
Yes. So what I'm using, the vocabulary I'm using right now, is coming from graph theory. Okay. So we have a graph. Here it's a two-dimensional graph, it's a plane. It's a particularly simple one because it's a grid, okay? But you could think about a generic graph, okay? And here this first sum means that I sum over all edges. That means the pairs of vertices or nodes that are connected on this graph. And the second sum is the sum over all nodes, all vertices, okay? Which means here, in this case, over all locations.
So for the first summation, I cannot be equal to J.
So no, we will, no, I cannot be equal to J, okay?
So I here is similar to I in the second. So
This I in these two sums, these are dummy indices. If you write sums, you can change the symbol to whatever you want. These are just, but the interpretation is the same, yes. But it's like in mathematics, if you do an integral over dx of some function of x, you can rewrite this as a di of the function of I. At the end, it's nothing. This is a dummy indices. If you sum like this, it's just a dummy indices. But this I has the same interpretation here and there. Here I'm summing over all pairs of vertices that are connected by an edge. Okay? And I will always assume, if I'm not saying otherwise, that I identify ij with ji. So these pairs are not ordered. It means that it's the same to consider summing over that close to that or that close to that. You don't sum it twice. It's not an ordered pair. Okay? All right. So now I would like with you to try to discuss a bit physically what do you think would happen if we start to change this j and mu. First, how can we interpret this j and this mu? So let's start with the simplest one, this mu. So how do we understand what happens? So we remember that now we have a system that is described by this Gibbs measure, by this Boltzmann distribution, which is exponential minus beta h x j mu over z. So you see that this minus and these minuses, they simplify. So at the end, let's write explicitly. Okay, so I don't need to rewrite explicitly, they simplify. So what happens? Let's say that the temperature is fixed. What happens if you change mu? Let's say that mu is getting bigger. What do you expect? If mu is big. Speak louder, because first I need to hear you, and then the others also need to hear you.
So the second summation is for all those particles.
We're summing over all positions.
Anywhere.
Everywhere. We're summing everywhere over the whole grid.
And
we remember that the interpretation of this xi is that if it's 1, there is a particle. If it's 0, there is not.
So the Hamiltonian is basically telling you about the energy of that particle, right?
Yes. So each time there is a particle at some location, it
is 1, and there is
decreasing a bit the energy.
Because they are
If what? I said nothing about this mu. Maybe this mu is positive or negative, I don't know.
No, we don't know about mu. But
So let me write in general mu belongs to R and J as well. It can be positive or negative number. So now what I want you to think about is what happens when there are 4 scenarios. J positive, mu positive, J negative, mu positive, J, etc., etc. I want the interpretation of these various cases. Let's start with the first one. J positive and mu positive. So let me come back here. So if mu is positive, this term is favoring what? So for the others, when I say this term, I mean this term. What happens when mu is positive? What does it favors?
The particle being anywhere?
Anywhere in
the
to be there.
Yeah.
Yes, so this mu is actually called a chemical potential. Okay? Because here, in a sense, even if the measure we're using, the Boltzmann distribution, because these xi are interpreted as particles being there or not, the number of particles can change, and this mu is controlling the number of particles on this surface. Okay? And you see that indeed, if this chemical potential is positive, minus times minus get a plus, so the probability will be bigger. Okay, the exponent here will be bigger if this sum is bigger. Right? And this sum being big means that you must have many particles on the surface. Okay? Do you understand or?
Yeah.
Okay. All right, so now if mu is negative, that's the opposite. This energy will try to, this term will favor sparse configurations where you have very few particles. So this is a kind of energy cost for the particles to be on the surface. Depending on the sign, it will favor, it will attract particles on the surface or repel them. Okay, so if mu is positive, you see that the energy is minimized, gets lower when you have many particles, so it's an attractive potential, kind of attractive local potential on each location. While if mu is negative, it's the opposite. It's like you have a repelling effect. The particles do not want to get on the surface. Okay? All right. But if you had only this term in the Hamiltonian, you see that the system would be very simple in a sense, because you would just, if you want the probability distribution, the Gibbs measure here would be factorized. The particles would be independent. Because you see that the exponential of a sum is the product of the exponentials. And we said that when we have a product over the variables, if the joint distribution here is the Boltzmann distribution, becomes the product of marginals, which are depending each of them on a single variable, it means that the variables are independent. And so the system is very simple. You just need to describe one of them because they're all statistically equivalent if you have independence. Okay? So what makes this system richer is the second term. The second term, which are pairwise interactions, they create correlations between the particles. Okay? The joint law, which is this Gibbs measure, does not factorize anymore. You cannot write the Gibbs measure here as a product over I of some function, let me call it fxi over a zi. This is not true because of these pairwise interactions. If this would be true, which is the case if j is equal to 0, if you would have equality, then the particles are independent. But these interactions are coupling them. This is a coupling term, and which is what makes the system complex. This is what will generate the appearance of phase transitions, etc., etc. You need interactions between the elementary components of your systems, which are here particles, in order to observe complex phenomena like phase transitions and things like this. So, it's nice that you write, excuse me, professor. But you can call me Jean. I excuse you. Where can we find the recordings of the lecture? I don't know. Okay. I don't know. I will ask to Antonio. I will get this information. Do you know How I Met Your Mother? Yes?
Yeah.
I've seen 2 days ago the episode where there is Ted Mosby giving his first class and he starts to write professor on the blackboard and he doesn't know if he has to put 2 F or 1 F. And like he's like blanking like this and one of the students help him, you know, and it's like, and actually, Anna, there is just 1 F and 2 S at professor. Now I know, but I would not have been sure otherwise. So thanks, Netflix. Okay. So what is the interpretation of this J now? So we've seen that if it is 0, the system becomes trivial because the particles are independent. They decouple. Okay. But let's say that now J is positive. What does it favor?
More
connected.
Sorry?
More connected.
More
complex.
Connected.
connected?
Yeah, connected.
No, I think you're on the you have the idea, but it's not the proper word. What do you mean by what more connected?
More particles are near each other.
Yes, it tends to cluster the particles. Okay? Because you see that here I'm summing over neighbors. So if 2 particles are at least separated by 1 empty position, they do not interact. This is a close by interaction, okay? While if at 2 sites you have a particle and this J is positive, then you get 1 times 1 times J with a minus, so the energy is lowered. So it means that the probability of the associated configuration will be higher. So this term is tending to cluster the particles together. Okay? While, by opposition, if J is negative, it tends to repel the particles. Okay?
That means if J is small, all the particles try to be near.
So if J is positive, the higher J is, the more clustered will be the particles. Because let's consider the limit where J goes to infinity. Also, one nice reflex that I advise you to keep in mind. So the first one is try to explain to someone that doesn't know. And one is, in physics, it's always good to consider limits, the extreme cases, to understand what is happening. Because in between, you know, it may be difficult to grasp what happens. While in the limits, 0 temperature, infinite temperature, 0 J, infinite J, you understand much better what is going on. Because it's an extreme, so, okay? So for example, in the limit where J becomes extremely large, and mu is fixed, then this term will not matter anymore. It is vanishingly small with respect to the first term. And you see that it will, the energy will then be lowered by a huge factor if you start to have particles that are close by. Because each time you have 2 particles that are close by, that are neighbors, you gain an exponential minus J, you get a minus J in the energy where minus J is very, very large, negatively. Is it clear? Yeah. While if J is extremely large in the negative direction, you see that each time you have two particles close by, the associated configuration is much less probable. Yes?
Isn't it the opposite?
So maybe it's the opposite.
It is the opposite.
Yeah, so I don't know what I said, but it's the correct.
Okay.
It's the correct. So if J is positive, you want to have non-zero terms here. So you want clustering. If J is negative,
No. Isn't it opposite because of the minus sign?
no, but exactly. If J is positive,
Yeah.
More.
what you want, the configurations that are more probable are the one with lower energy. You see this minus sign simplified with this minus. So I think what I said was correct. So this term, when J is very positive, it tends to cluster the particles. While if it's very negative, it tends to repel the particles. Okay? And so now if you consider mu and J that are of the same order, so they both matter in the Hamiltonian and they have different signs, you start to have competition. It starts to be rich, the behavior, because, for example, if mu is positive, then this chemical potential is attracts particles on the surface. Okay? But let's say that J is negative. These interactions, it's like if you had particles of different electrical charge that are trying to repel each other. But if they repel each other, it means that quickly you will fill in the whole surface and you cannot anymore add new particles. So this term is not happy. You see, so there is a competition between the two. While if this term is a repelling term and this one is clustering, there is again a competition because you want particles to cluster to gain energy, which means that you need to have particles, while this one is telling you, no, I don't want any particles to be on the surface. So it's this competitive behavior that will generate a rich phase diagram, different phases described by different order parameters. Like, can you think about an order parameter in this case? One way to describe the system at the macroscopic scale. What could we think about?
Excuse me, Professor.
Yes.
Online student can't see the board when you are saying things, and we cannot see. We can only see the blackboard.
Yes, okay. So I was just describing the competition between this term and this term. I'm just saying that in the different scenarios where one is positive, the other is negative, and so on and so forth, you have competition between these two terms.
Thank you.
Yeah. So it's written in detail in my notes. If you miss something, I will try not to do that again. Okay. So one order parameter could be what here? Could be, for example, kind of magnetization, which is, if you want, what is that? It's the expected number of particles. It's the number of particles, it's the density of particles on the surface. So depending if it's high or not, maybe the system is in one state or another one. Okay. But actually, you would need probably something a bit more subtle to describe what is happening, because we said that we may have clustering or not. Okay, so maybe you want to look also at correlations between particles. Okay, so maybe a more another parameter that catches more information could be this. And if you want, you can center it. See that this tells you this is large, then you know that the particles are clustered. If it's not, they're not. Okay. This is a correlation. Okay, the pairwise correlation. And so depending on which information you want to describe about the system, here you want, for example, the first order parameter would catch the density, the other one would catch this clustering effect, then you need to define different quantities like this. But you see what is important is that, sorry here, what is important is that these quantities are macroscopic quantities. They are summed over the indices, the particles. They do not depend on specific I or J. Okay, they are global quantities. Okay. Okay, so now the Ising model, which is nothing else than the same model, but with a slightly different interpretation. Oh, I could have okay, so here I write it in red because this is the absolute model you need to know about. You can spend a career studying this model, and you can use this model to model whatever you want, essentially. You will see that it appears a lot in this review article I sent you. So the Ising model is defined by this Hamiltonian. Now I will keep implicit the dependence in the parameters J and H that will appear, for example, here. So now we're not necessarily considering a grid. Now we're considering a generic graph of interactions between particles, which is defined by this set of edges. Okay. And let's make the thing even richer. I will be coherent with my notations in my notes. And this is the usual notation we use in physics for spins. Here, here the sigma belongs to the following configuration space. The variables are binary. We have n of them. So binary variables in physics are called spins. But you can it represent any generic binary variable, so it doesn't have.
The spins then?
Sorry?
Are these the spins of like particles?
So the Ising model has been originally defined to model what we call ferromagnetism. So ferromagnetism is the fact that if you take a material which is made of atoms that possess a quantum spin, which you can think as a kind of little magnetic orientation. Okay, the preference in pointing in one or the other direction, depending on some external magnetic field. What happens is that if you take such an assembly of atoms, and if the temperature of this material is not too high, so below what we call a critical temperature, below a certain phase transition, the spins will globally align together. There will be an extensive fraction of them. By extensive, it means a linear in n fraction of them, which means a linear fraction of them. Is it clear? Linear function of them. It means that alpha n of them, where alpha is a fixed number less than 1 and greater than 0, but that does not depend on n. Okay, so let's say it's 0.5. Will align, will be essentially most of the time in the same direction. Okay, and this will create a global magnetization as measured by the magnetization that I wrote just before. And so when you have a magnet that you put on your fridge, this is because these variables, the atoms composing this material, possess a spin and are below their critical temperature. And therefore, they generate a global magnetization, which in turn interacts with the atoms in the other material. They can bound. But if you take a magnetic material and you heat it a lot, then the temperature at some point, the fluctuations due to the temperature will win, and you will not have anymore a global magnetization. The system is not anymore ferromagnetic. Okay, so we will see that. It's just a spoiler. But what I'm saying here is new to all of you?
No.
Yeah. You don't know. You don't know if it's new.
I encountered it.
Sorry?
I encountered Ising.
You encountered this. Telling me yes, telling hello from the next time. Yeah, no, I think you probably heard about it, but
Perhaps we didn't know the name of it.
okay. This is also called, in the case where J here is not a function of the locations and H either, so in this specific case that we'll look now, so here is a configuration sigma. So in the specific case where you sum over all pairs ij, so there is no underlying graph. It's like if each spin is interacting with all the others. So now I don't put any more set here, or this sum I could write it like this as well. I less than j, I sum over all possible pairs of indices with a j which is outside of the sum, sigma I, sigma j, and sum of I 1 to n, with a h outside of the sum sigma I. This is called the Curie-Weiss model, which is an instance of the more generic Ising model. And this is the model of ferromagnetism. The simplest possible model of ferromagnetism. So you see, what's the main difference between this generic Ising model and the Curie-Weiss model, which this Curie-Weiss is, by the way, quite close to the previous lattice gas that we've seen, and actually there is a direct mapping between the two systems, and I will tell you right now. You see the difference is that here, these JIJs, which are interpreted as local energy contributions, now they are local, they depend on I and J, on the locations. Okay? It's like if on each edge of the graph, you have a small energy, you have an energy contribution quantified by this Jij, but it depends on which edge you are considering. And here the external field also depends on the position. Just like if you have a non-uniform external field. Okay? While in the simpler case here, the interaction strength between spins is the same for all pairs, and the magnetic field is homogeneous. It's constant. Okay? And the third simplification is that here I'm summing over all possible pairs. While in the generic case, which is here, I can sum over a generic set of edges. Maybe there are some of the spins that interact, some others are not interacting, okay, as defined by this set E here. While in the simpler case here, they all interact with all the other ones, okay? So everything is very homogeneous. We have a homogeneous interaction, homogeneous external field, and everyone interacts with everyone. So you cannot think about simpler. Yes, you can think about simpler, which is when J is equal to 0, but then everything is decoupled, it's not interesting anymore. So the simplest model of coupled particles, by coupled we mean interacting particles, is this one, okay? And this model exhibits phase transitions. So even if the model is simple, as long as you have coupling, which means interactions between the variables, you will see phase transitions in the limit where you have many of these particles, of these variables, okay? Okay, so let's interpret again, like what we did before, the meaning of this J and H. So if this J is positive, what does it tend to be, to do?
In the generic or in?
No, in the simplest case, in this case here. Let's consider the Curie-Weiss model. Just one word, this type of model where the interactions depend on the locations are called disordered systems. Okay? It is a disordered system in the sense that the energy terms themselves are non-trivial. They depend on the locations, and maybe there are even random variables that have their own probability distributions. But with respect to these spins, here, for them, these variables are fixed, okay? But maybe they were fixed to some random value drawn from some distribution, and therefore we call this type of system disordered system. And this is a whole field of statistical mechanics in itself. And if you look at the paper I sent you, you will see that these are the types of model that you can map, that you can connect naturally to many, many problems in statistical inference, in signal processing, in machine learning. Okay, so these are very generic models, very powerful models. But let's consider the, I was going to say baby model here, but this is not a baby model at all. It contains already a very rich phenomenology. So what happens when H is positive? What does it favor? No.
Positive.
Sorry?
Positive spin.
Speak louder.
If H is positive,
Yes.
the probability is higher if the spin is positive.
Exactly. So if H is positive, then the energy will be lowered when the spins are in the upwards direction. And so this, while if H is negative, it's the opposite. So this external field is, so the external field, the H, is a term that wants the spins to align with. So if this external field is positive, the configurations where the spins tends to be in the upward direction will be favored. while if H is negative, it's the opposite. And the higher the magnitude of this external field, the stronger its effect. Okay, so you can see this H is a control parameter. It means that you as a physicist in a lab that is experimenting on these spin systems described by this Hamiltonian, you can change the value of this external magnetic field, and you can see what happens. You can act on the model, on the spins, by changing this value. Again, we're physicists, how to think, we look at extremes. If H is going to plus infinity, the interactions do not matter anymore. The spins need to be in the ground state, because if H is going to infinity, it's like also if beta is going to infinity, it's the same. So we have a parameter in front of the Hamiltonian that goes to infinity. So the system will be trapped in one of its ground states, and actually in this case there is just one, which is the ground state where all the spins align in the same direction. Not a single one is down, they're all aligned together. Okay? In this case, this is the positive, the upward ground state. If H is going to minus infinity, while J is fixed, all the spins will point downward. So you can control the system like this, and so H is called a control parameter, or external parameter. Okay? Now let's say H is fixed. What happens with J? So in the sense, this external field induces a direction, okay, a favored direction. While J is doing what? Same? If it would be the same, there would not be two terms.
The spins will be
They will take whatever value they
same.
Sorry, when you say same, you mean?
The spins will be the same.
Will be aligned together. Exactly. So you see now, because you have a product between two spins, what matters is not the individual values of the spins. What matters is the product. So what matters is whether they're in the same direction or not. So if J is positive, the energy will be lowered if the sigma A and sigma J are of the same side. So they want to align. But you see, you have if we forget this term here, oops, I don't want to forget it that much. Let's say we forget for an instant this term, H is equal to 0. You see that this Hamiltonian has a symmetry. It has a up-down symmetry. It means that if you take any configuration and you reverse it, you reverse all the spins, it will have same energy. It has the same probability to be in the configuration where you have this spin like this spin like this, and this spin like this, or like this and like this. Okay, this is a symmetry inherent, intrinsic to the Hamiltonian, when H is 0. Okay? So when H is 0, the Hamiltonian of sigma, the energy of sigma is the same as minus sigma if H is 0. Okay? This is called the up-down symmetry, or flip symmetry. But when H is not 0, you break this symmetry. Okay? So the first term, proportional to J, is indeed trying to align the spins together.
That's not visible.
Sorry?
It's not visible.
So I just wrote that H of sigma is equal to H of minus sigma if H is equal to 0. There is no external field. Okay?
Yeah.
So, so this J positive is trying to align the spins together. So in this case, when J is positive, we talk about a ferromagnetic interaction, because it tends to align them, and therefore to create ferromagnetism. Okay. While if J is negative, we talk about anti-ferro interactions. So if J is negative, instead, the Hamiltonian is lowered when the spins, they anti-align. Okay, so if J is extremely negative, the only configurations which have a non-negligible weight, and by weight I mean probability weight, will be the ones where there are approximately half up and half down. Okay, you will have a random configuration like this where there is no global ordering, because this J wants them to anti-align. So you see that by changing this J, you can go from a phase where you will have many spins that align, which will be described by their magnetization. You will see that if you define the magnetization, if this thing in the limit when n is very large, m is positive, then you are in the ferromagnetic phase. Okay, you have a global ordering of the spins. If instead it goes to 0, you have an anti-ferro magnetic phase. You are in the anti-ferromagnetic phase. Okay, and in between, something must happen. And when something happens in a complex system, it is a phase transition. Right? So here, note that it is equivalent to tune the values of J and H, for example, or the temperature. While, for example, if you forget this term, you see that it is redundant to have both the J and the beta in the exponent, because beta J, you can just give it another name, and it's a new parameter. Okay? So, what I'm just saying is that you can go from ferromagnetic to anti-ferromagnetic phases, or by tuning the temperature. At high temperature, you will be in the anti-ferromagnetic phase, because it's like having a small J. Okay, and the fluctuations will win due to the temperature. It's like the measure will become flat. While at low temperature, the J positive, you will get ferromagnetic. So I'm just, maybe what I'm saying right now is just confusing, but I'm just saying that sometimes you can think, you can move around in the phase diagram by or changing the temperature, or here that could be the interaction strength. Okay. You can act on the system in two different ways, but the result may be the same. Okay. Okay. So convince yourself that actually the lattice gas that we define is equivalent to the Ising model because you can just redefine the Xi's that belongs to 0, 1 in the lattice gas as 1 minus a spin, or equivalently, a spin is 1 minus 2 Xi, or that's the same as minus 1 to the power Xi. And therefore, by a simple change of variable, you go from the Ising model to the lattice gas, or vice versa. So if the two Hamiltonians are the same up to a change of variable, actually it means that the two systems are the same. They have the same phase diagram. It's just two different interpretations of the same system. Okay? So when we were talking in the lattice gas about clustering, we were saying that when it was called the J, it was a J also, no? Yes.
Yeah.
When the J was positive, then the particles were tending to cluster. It's just saying that in the Ising model, when J is positive, the spins tends to align. So you will get regions of spins that are aligned, that you can just think as clusters in the lattice case. Okay? Okay, so I invite you to read a bit the notes where I say a bit more things, and that will help you to clarify. Just one remark from there, why not you go beyond and define what I will call a generic binary system, which is a kind of natural generalization of the Ising model, which is an Hamiltonian. I will take x, generic variable x, in order to emphasize that they are not necessarily -1 and 1. They can be 0, 1. Okay, so what's that? Here, A is any subset of vertices, okay? So maybe in this subset, there is just one vertex, sorry. In this case, it's just a local term, like an external magnetic field. Maybe in this set A, there are two variables, in which case this is a pairwise interaction. But maybe there are 3, 4, 5, 37, whatever you want. This is a generic way of writing interactions between spins. Okay. And because these variables are binary, the only thing that matters here is their product. Okay, so it's a generic form of Ising model, if you want. Okay, and this JA is the interaction associated to this small subset of spins. Okay, this is a very generic form. You can rewrite the two models that we considered until now in this form. Okay, in this case, all these subsets A would be pairwise, would have a cardinal equal to 2. Or to 1 if you have also an external magnetic field. Okay. So for example, one instance of this could be a model where you have actually interactions, 4 body interactions. And we call this set P the set of all 4 body of all tuples with 4 spins. It's called like this, tuples. Very nice word. Okay. This is one example. Okay. In this case, all the sets, they have cardinal equal to 4. Okay. So this is just to emphasize that these formulations are actually extremely general. You can write tons of different models with the same formulation. Okay. Okay. Are there, so what I want to do is the last 15 minutes, maybe I have time to discuss an even further generalization, which will be actually the ultimate generalization of discrete Hamiltonians, with which you can describe whatever you want. That's fancy. But before doing that, do you have questions on what we did? No, everything is. But it's a no because you're lost, or it's clear.
Yes.
You can be honest, no? It's clear.
Yes.
Okay.
And the exercises are making more sense now.
Yeah. Okay. All right. So now I want to define a notion which I think is useful for you to know. Point. Which is called factor graph. Which is, if you want, the generalization of Ising models, but to variables that can be arbitrary. Maybe they're not just binary. It can be whatever you want. So, what is the most general form? Essentially, what I want to discuss is what is the most general form of Gibbs of Boltzmann distribution you can think of. Okay. So this form of exponential minus beta h is extremely generic. But is there a kind of it's not more general what I would present. It's an alternative way of thinking about the Boltzmann distribution, which is an equivalent way. Okay, that's just what I mean. So what we call sorry?
E power x exponential function.
Yeah, so I will just, if you want, I will approach the Boltzmann distribution from a slightly different angle. That is a nice constructive way of constructing very generic distributions, and we will see that this is equivalent to a Boltzmann distribution. Okay, it's just another point of view on these high-dimensional probability distributions, which is the case for the Boltzmann distribution. High-dimensional means it depends on a vector of variables of high dimensions. Okay, n is large. Okay, so and also it's not only an equivalence, but factor graphs is a very powerful way of thinking. It's a graphical way of representing complicated probability distributions, and once you have this visualization, this graphical representation, it allows to actually write algorithms and to do computations in an easier way. Sometimes it's nice to draw things, for example, Feynman diagrams. A lot of things that have been discovered just because Feynman understood that you can do complicated computations by drawing stuff. And this opened the whole field. Okay, many discoveries are based on the fact that we managed to write integrals using simple diagrams. Okay? And having a new formalism, even if it's equivalent to using integrals, it simplifies so much the way of thinking about the problem and the way of doing computations that actually you discover new things, even if it's equivalent. So factor graph is a beautiful way of representing complicated probability distributions like the Gibbs-Boltzmann distribution. Okay. So a factor graph can be associated to any distribution that we call a factorized distribution. And by factorized, I do not mean here that it's really factorized over each variables. It's not that the variables are independent, but there is a factorized structure. So what I mean by that is that the distribution I will consider take this form. I will write once all that as vectors, but from now on I draw up again the vector notation, okay? We're always talking about vectors and we're doing statistical mechanics and we don't write probability for single variables. Okay, and of course the partition function is the sum over X, the configurations that belongs to their generic phase space, that can be whatever you want. In my mind, all that is always discrete. In the continuous setting, things are a bit different. So we will restrict ourselves to continuous variables. But maybe each variable now can take 25 different values, not just 2. They're not necessarily binary. Okay. The cardinal here of sigma, the variable belongs to sigma, where this is generic. The cardinal here is generic. So these are generic discrete variables. Okay. So these functions are called factors. Okay. And for a good reason, it's because the overall distribution that you are considering is factorized over these factors. It is written as a product of factors. So we just call them factors. Okay. And the point here is, you see, I will, let me just require that these functions are from, in general, this can depend on any, let me call any A, which is a subset of this, and it will output a positive number. Okay, we want these factors to be positive. Why? Because it would be weird to have a probability distribution with negative values. Okay? Well, if we ask these factors to always be positive, because we have a partition function like this object is normalized, and so this defines indeed the probability distribution. Okay? So these factors, they are also called compatibility function. Compatibility functions. And why is it called compatibility function? To be clear, try to guess the names we give. So
The compatibility between the...
Exactly. So essentially, you see that here by XA, I mean this is a subset of the variables. Okay. So often in the models that we will consider, this subset are small subsets with few variables. For example, in the Ising model, we were considering only pairwise interactions. So each of these factors, which was an energy contribution in the Hamiltonian, was depending on just 2 variables. But in general, it may depend on more variables. Okay? But it always depends on few of them, not extensively many. Okay? It's not always true, but in this class we will consider this. And essentially this factor is a function that takes positive value, and the point is that the higher the value of this function, the higher will be the product, and therefore the higher will be the probability of the associated configuration. Okay? So if all these factors or these compatibility functions have high value, it means that the configurations is compatible from the point of view of all these factors. And then taking the product, you get something with high weight. And so it has high probability. Is it clear? While, let's consider an extreme case again. If even a single, let me authorize these factors to be 0, even if a single of these factors is 0, it kills the associated configuration. The associated configuration has 0 chance to occur. Okay? So essentially, this probability is trying a system that fluctuates according to this probability, is trying to be in configurations so that as many as possible factors are satisfied, in the sense that they have high value. But maybe there are some factors that will tend to favor some specific values of their associated to their variables, while other factors that also depend on this variable will favor something contradictory. So you may have contradictions, and this is what generates the richness of this system. You may have contradictions. It's not that all these factors will align the spins, if you want, in the same directions. You may have what we call frustration in physics. It means contradictory information coming from different factors. Maybe for a given spin that appears in 3 factors, let's say, the factor number 1 is happy, to say that it has high value when the spin is up, but this one wants it to be down, while this one wants it to be up. So you have a frustration. You cannot find a configuration where all of these factors are maximized. And this generates the richness of the model. So all these contradictions. Okay? Okay, so let's do something trivial, and then we stop and we will continue next time. But again, sometimes trivial manipulations allow you to see things better. By the way, these theta's here that I didn't describe, they represent possible parameters that appear in this distribution. You remember, like the Jij's in the Ising model, these were parameters appearing in the Hamiltonian. Here by theta, it's a generic notation to mean the vector of all parameters that appear in this distribution and that are not the variables. Okay, I distinguish between the variables x that fluctuate according to this probability distribution and the parameters entering this distribution, which are these theta's. Okay? These theta's are just Jij's, they are interactions. Okay? They define the interactions. We will give many examples. But you see that if I write a given factor, and so here let me write explicitly, xa is a vector that is essentially a subset what I want to write, yes it is, let me write this explicitly, xa is xa1, xa2, so it's a small vector like this of a subset of variables. So what I can do is just take the exponential of the log Okay, it did nothing. But now, if I do that, and I rewrite my factorized, I don't like to say factorized because it seems like things are independent. But this type of distribution using just this exponential form, what do I get? I have a product over A of this exponential of this log. Let me just write FA, and by FA I mean, okay, I will write like this still. I drop the dependency in theta A to make it simpler. 1 over Z, and this is 1 over Z exponential of minus sum over A log of 1 over FA XA. And magic, here we just defined an Hamiltonian. Okay? And the inverse temperature, in this case, beta is equal to 1. Okay? So you see, you can think of these factors, and to be more precise, the logarithm of the inverse of a factor as an energy contribution in the Hamiltonian. Because you see, here we have a sum over this A, and each log of 1 over FA can be interpreted as one term appearing in this Hamiltonian. And actually, it's very natural to have this log of 1 over FA, because, okay, the log is an increasing function, so it doesn't change the behavior. What matters is that we have a 1 over FA. You see that if a factor is happy in the sense that it has high value, then 1 over FA is low. The log of something low will go to minus infinity, or will go to something, will go down. You take again a minus, so it goes up, and therefore it participates, it favors the configuration. So this log of 1 over FA is very naturally interpreted as a term appearing in Hamiltonian. Okay? So it looks like we did nothing, we just rewrote like a generic probability measure in an exponential form, but now we have a very nice interpretation. And actually what I will do next is to, so let me just end on that. Now if you define the Hamiltonian as a sum of local energy terms, then this E of A's are the log of 1 over FA XA. Okay? So we just realized that a very generic, an extremely generic class of probability distributions can be written in a Boltzmann form. Okay? And therefore, it kind of suggests very strongly that studying Boltzmann distributions, which is the goal of statistical mechanics, should have a much broader applicability than just studying particles on the surface. Because you can easily imagine that with this extremely generic form of probability distributions, you can model tons of things. Okay? Not just Ising models. You can think about whatever you want, but there is probably a way to cast it in this language. Okay? All right, so next time we'll see how to draw this distribution, to exploit this local structure, to make drawings and to have a visual representation of this distribution. Okay. any question by anyone? By the others or? Okay. So tomorrow, same time.
Thank you.
Ciao.
Thank you, bye.
No.